agreeing to give a talk. Professor Michael Hesse is the Director of Science at NASA Ames Research Center. And his research area is theory and modeling and kinetic space plasma process. And also he's has research area as a space weather related topics. Professor Hesse was also shortly in the University of Bergen, Norway, where he led the Geomagnetic Expert Service Center, and which is a consortium providing space weather service for ESA. But actually, he has been long served as a NASA Goddard Space Flight Center as a director of Heliophysics Science Division. And I think he spent almost 25 years there. And I think everybody possibly know this Community Coordinate Model Center, which is called CCMC in the area of space science. And he's the founding director there. And so he's also the father of this modeling activity, which you might have heard a lot in the area also in the space weather, as well as space science, planetary science, magnetospheric physics in the Earth, and so on. And he's, of course, what you can see in the title, he's very much involved from the beginning of the mission, Magnetospheric Multiscale mission. And he's actually the co-investigator lead for the theory and modeling. And he's a fellow of AGU, American Geophysical Union, since 2010. And he got the prize, the Space Weather and Nonlinear Waves and Process Prize for the American Geophysical Union in 2019. And actually, he's originally from Germany. He graduated from University of Bochum in theoretical physics division from Ruhr University in Bochum. I'm sorry, so Ruhr University in Bochum. And so Michael has 290 papers in space plasma physics, theory, modeling, as well as the space research related topics. And so he will give us today this nice talk. How does magnetic reconnection work? What we know and what we don't. So please, Michael.
Okay, well, thank you, Rumi, for this long introduction. I'm always thinking if somebody gets such a long introduction, it means they must be quite old. And so it gives me something to think about here. Okay, but thank you so much for having me here. So I'm going to tell you a little bit about what magnetic reconnection is, what we have learned because of the MMS mission that you're seeing here schematically on this first slide. And then if time allows, I will also talk a little bit about what we don't know yet and what we can research. So as I said, we'll start. What is reconnection? Why do we actually care about it? What were our expectations before we had this mission, and what this mission discovered? And as I said, some open questions and so on. And you can see down here, this is in Goddard's big clean room, where these 4 spacecraft, you see more of that a little bit later, were stacked on top of one another in one of the pre-launch tests that we did. So okay, so I would be remiss not to acknowledge that there's a rather broad based community that's engaged here, very international, various countries, including from Austria, in this MMS endeavor. And you perhaps know that your own institute is actually providing, has been contributing quite significantly to the hardware for this mission. Okay, so let's start very easy, and we're going to get progressively a little bit more complicated. So as you know, space, and we're not quite as close to the sun, fortunately, otherwise life would be a little less comfortable here. It's shaped by the interaction of electromagnetic fields and charged particles, which influence each other. And there are certain rules governing this interaction, and magnetic reconnection is one of those fun things that actually breaks rules, okay? this is always fun. If there's a rule, how can you break it? And reconnection does that. Okay, so let's talk about this rule. What is this rule? And it involves the interaction of fields and particles. So let's look at reconnection in the context of when it doesn't happen. Actually need to get your nice pictures a little bit out of my way here so I can see my own slides. So reconnection actually does not take place if you have two plasma elements. This could be electrons, protons, or other ions or so that are connected by a magnetic field line at some point. So you follow the magnetic field along this path here, and you end up by another plasma element. They stay connected like this even at a later time, and they do that for any of those. So this is the velocity of these plasma elements. And if time progresses this way, then at a later time, for any such two plasma elements that you pick in the space of interest that are initially connected by a magnetic field, and they're still connected by a magnetic field line later. Very simple concept, happens most of the time, as a matter of fact, but it has very significant consequences. Okay, one of those consequences is the following. Whether we call that frozen influx or magnetic line conservation for obvious reasons, because it conserves the magnetic connection, the line, if you want, between two plasma elements. So this has significant consequences. So what happens if that holds? So let's, and this, okay, I can't see my own slide. Can I make this go away here, maybe? I can, very good. So here we go. So this requires that E, the electric field, plus this velocity that I just drew here, crossed into the magnetic field is equal to 0. That's a very simple condition, which we also call ideal Ohm's law. So if this condition holds, and this is satisfied at all times, and magnetic reconnection doesn't happen, and you don't know what that magnetic reconnection is yet, but I'm going to tell you what happens if this condition holds. So here we go. Here's a sketch of our magnetic field of the Earth. The sun is off to the left here. This is a solar wind here, particles and magnetic field coming from the sun. Here's the bow shock. This is the magnetopause, here the boundary of the magnetic field that belongs to the Earth, if you want, and the interplanetary magnetic field. And then we have a drawn out magnetic tail on the night side here. Okay, we know that there are lots of particles that are coming from the solar wind. We can detect that with our detectors. So if we have two plasma elements here that are sitting on this field line here in the beginning, okay, then this rule says they got to stay so connected at any time. So if they were to end up in this situation, you can see they're not on the same magnetic field line anymore. You cannot draw this connection by means of the magnetic field. So unless magnetic reconnection happens, this thing is forbidden. It cannot take place. Okay, so reconnection is about violating this rule. So we can actually get plasma from the solar wind, from the sun ultimately, into the Earth's magnetosphere. Okay, and similar with other objects in the solar system and in astrophysical systems. So let's just, the next thing we then do is, well, okay, let's say magnetic reconnection is a process that allows that to be violated. Okay, so it changes, well, plasma can change magnetic connections, okay, by means of something that's localized. And we call that a localized non-ideal electric field. And you're going to see more of this throughout this talk. So specifically, we want to have this situation here, okay, where these guys are connected initially, okay, and then it's a later time they're not connected. And in the middle, something magic is going to happen in a place called the diffusion region, DR. Okay, and obviously, because as you saw before, this condition with an equal sign here forbids that. Okay, there has to be something on the right-hand side here that makes that possible. And we're going to be looking at that a little bit throughout this talk. Okay, so reconnection is just the process that makes that possible, but it doesn't, shall we say, mess up your entire system here. It only does that in a very localized region. Okay, so what goes on in this region? You might wonder. That's what we're going to be looking at. So come back to our problem here. Magnetic reconnection is just thus the process that opens the magnetosphere here. Okay, so it opens it here, and then our happy particle here can go in here and enter the Earth's magnetic field and maybe even ultimately precipitate into the upper atmosphere, causing aurora. So good. So we have defined something that we need apparently. Now, what are its properties? And why is it important beyond what I already showed you? So let's look at a couple of systems where we believe reconnection is important, and look at its energy balance. So magnetic reconnection not only allows this transport that I just alluded to, but it's also a big energy conversion process. So if you start with stored magnetic energy here this is magnetic field here, and directed in opposite directions, to the right here and to the left below. And if you pile magnetic field together, then you're storing energy. If you just take two like poles of magnets, push them together, you're spending energy. That's storing energy in that field. And if you let them go, they fly apart. That's releasing that energy. Now, this happens in space too, albeit a little bit more complicated. So we have energy stored here, okay? And then something magic happens in the middle, and we got these two plasma elements here, and then something new forms here, new magnetic field forms. This magnetic field is reduced. Okay, and these plasma elements are sitting out here, and they're flying out to the left and to the right in form of a jet. Okay, and we'll come back to these jets later. So memorize that if reconnection is going on, you get a jet to the left and to the right, and it disconnects these plasma elements, but it also converts energy. As you can guess, if there's a jet, there's energy conversion. You can see that here. This is actually from a numerical model of particle and cell simulation. This is the energy here, and time is at the bottom. And you see the magnetic energy here wobbles around a little bit, and then it starts to decrease. And it goes into internal energy, which is basically heating, if you like, and then into kinetic energy here, which is related to these jets going to the left and to the right. So we're converting magnetic energy into particle energy, which can be directed or non-directed if it's thermal heating. So this is what it does for you, and it does it in a lot of places. For example, there's now there's a paper in 2015 that actually believes that some of the emissions that you're seeing from the Crab Nebula, and I realize some of you know this much better than I do, might be the result of magnetic reconnection, which takes turbulent magnetic fields that are in this post supernova region here and collide, and in the way that I just showed you, and release energy that then leads to these emissions. On the sun, a little closer to my territory, if you like, we have these eruptive events here. This is this beautiful magnetic structure here, as some of you know very well, can be suspended there for very long times, and then suddenly released by the release of magnetic energy that's being created by motions in the solar surface here, in the solar photosphere, basically, that bunches magnetic fields together, again, creating energy that can be released. And these things fly out into space with dramatic consequences. If they were to hit Earth, for example, the space weather effects that Rumi mentioned can be quite dramatic. So, and here's an example. This is our magnetic shield again, our magnetosphere, and you can see what a model says will happen if it's impacted by one of those eruptions. You can see it erases the day side here, it compresses it significantly and causes a lot of activity on the night side, including pumping up radiation belts and so on and so on. And this is all mediated by magnetic reconnection, which allows the energy transfer from the solar wind into the magnetosphere, together with the plasma transport that I alluded to at the beginning. So very important. And it also plays a role in laboratory devices. It plays a role in tokamaks, for example, where it can cause disruptions and loss of confinement that you don't want if you're studying fusion. So as a result, in laboratory, the laboratory experiments like this one in Tokyo here, the TS4, that Ono-san in Tokyo is operating, which tries to model reconnection in the laboratory to understand actually how to prevent it from happening, really, to understand its physics with the goal of preventing it from happening, to keep confinement alive in fusion devices. So with this very, very quick introduction, I hope you are with me in accepting that reconnection is really a key process in plasmas, particularly, of course, in collision with plasmas. And it has hence been a research focus for many years in laboratories in space physics, and also in some cases in astrophysics. But we didn't really know how it works because we didn't have the tools for it. At the core of its functionality is this electron diffusion region, the very core of the reconnection process. And we did have predictions of how it would work before MMS, and then we're going to see what MMS showed us regarding how it worked. So here's a prediction. Now, it's a needle in the haystack, and something that needle that moves the haystack, as a matter of fact. So the sun is on the left here. This is our the Earth's magnetic field, again here with the magnetopause, the boundary where reconnection occurs in order to allow particles and energy to enter the magnetosphere. And this is sort of a schematic that we did. It's actually part of the MMS proposal, original proposal, that shows you how difficult it is to understand magnetic reconnection. So the system size here, this is about 100,000 kilometers or so. And if we blow this up here, it could look something like this here, this little region. Then we add 500 kilometers, okay? And this central region here, where actually the action is, where this diffusion region sits, if we blow that up even further, we end up at 10 kilometers, and this scale size across here is just a kilometer or two. And the night side, it's a bit bigger, maybe 10-ish or so. But in any case, it's really, really small compared to this large-scale system. And we now need to build a mission that can actually not only find this, okay, but also study it once we have found it. Okay, and so these current sheets here, that this is a current sheet of electric current carried by the electrons. That's 1 to 5 kilometers thick, and it's wobbling backwards and forwards all the time at about 20 kilometers a second. So if you want to measure that, you need 30 millisecond time resolution for electron measurements. You actually need to measure all the electrons in all directions and all relevant energies within 30 milliseconds. That is roughly 2 orders of magnitude more or faster than any previous measurement has ever done. We can actually, now we know we can do even better than that. So it's quite remarkable. This was a requirement for our mission if we wanted to understand this process. And space really gives you the only way to do that because the sun is too hot, the astrophysics is too far away, and in laboratories, these scales are often millimeters or even less than millimeters. So you can't really build detectors very easily that measure them. In space, we can, and we did, and you'll see some of the results. So the MMS had its first target. What happens inside of this region? Okay, so let's start at a very basic look at sort of the physics of this region. And it starts with a reconnection electric field. If you talk to anybody who works in space plasmas or in plasma physics in general, and you mention reconnection, they think about reconnection electric field. So what is that? So the reconnection electric field determines the rate of moving things, and particularly magnetic flux, okay, from here to over here. It's by Maxwell's equations, very trivially, given by an electric field here. So you need to have an electric field that points out of the plane to move the magnetic flux from here to here. If there's no electric field, no magnetic flux motion, hence no disconnection, no energy transport, etc., etc. So this electric reconnection electric field, as we call it, is critical to reconnection. Okay, so we turn this sideways. Then it looks like this. Here's our magnetic field sticking out of the plane. Here's going into the plane. with rotated plane, we got an electric field here. And in this region, we got our little electrons. There's a bunch of electrons. And as you know, an electric field exerts a force on these electrons. So what happens with this force? Okay, you know, we have always axial equals reaxial. So what balances the force of the electric field? If you like, electrons in a voltage. Okay, this is as basic as it may seem now. The basic question that we had to solve, not that we quite understood how fundamental it was at the time when we started looking at it. Okay, so let's just look at some options here. Okay, so we got our electric field, we got these electrons as in this case, no magnetic field here, or the magnetic field could be pointing out of the plane here in the center. In either case, the electric field could straight line accelerate the electrons, which of course would lead to shoot them out of the area immediately or make them relativistic, something that we don't usually see in space. So one option here is this, what we call wave-particle interaction. So again, an electric field, I left out the magnetic field now. Okay, and you got our electrons, they get accelerated this way, and then you have fluctuating electromagnetic fields. So this E goes up and down, and the magnetic field wobbles around too, and if it does that fast enough, it can scatter the electrons in all which directions, and therefore, if you want, break them against the force of the electric field. And that involves special environmental conditions, which we find in some cases. There are a variety of possible mechanisms. Some of those we see in lots of places in space, but we don't see reconnection in lots of spaces in place. So there's not a one-to-one connection. And the question is, does MMS see this? So here's my little animation of this electron. So here's a 3D image of one of these reconnecting regions, which we sometimes also call X points for obvious reasons. Here's the incoming magnetic field, here's the outgoing magnetic field. So you would have jets to the right and to the left. And here's our electron. And now this region wobbles around, and this poor electron gets seasick and runs away in disgust, if you like. So this is one option. It was one of the two scenarios that we looked at when we wrote our proposal, as providing the, if you like, resistance against the accelerated force of the electric field. So let's look at the other one, and that we call mixing or transient orbits. And this is a little bit complicated, a little bit more complicated than the previous one. So here we got our magnetic field here. Our electric field is here. Now imagine the following situation. We got electrons coming in from above and coming in from below, and once they get in here, they get accelerated by the electric field. Okay, and they get accelerated a little bit if they've been there a short amount of time, or a lot if they've been there longer. But if once they reach a certain energy, they get ejected from this region simply by the magnetic geometry. And that in this case means out of the plane, which I can't draw very well. This is about the extent of my chartmanship here. So, but I'll try to animate it by clicking. So now we have these electrons here that have been accelerated a lot. Now they're gone. Some new ones come in. Some of the ones that have been here before get accelerated and leave next, and so on. And then you end up with basically a picture where electrons get injected all the time. They get accelerated a little bit and then they leave. Pretty much in a way a sandblaster works. If you've ever worked with a sandblaster, you blast sand in an airstream, which replaces electric field here, and it gets accelerated and leaves, right? So this is what the electrons are doing in this other model. Of course, the model is way more complex than this, but this is the basic idea behind it. And here is how that would look. So the electron comes in there, it bounces around a little bit, gets accelerated, and then leaves. Okay, so let's see that again. And this is, if you want, the one typical electron that is representative of a whole bunch of others. So what you can see here is, unlike the other scenario, the electron orbits here are quite regular. So it just bounces around here a little bit and goes to, and then eventually it leaves. So we have very nice regular orbits. Okay, so we had to decide which one of those is right, and that's what MMS was trying to do. So how did we test this idea? And I'm talking about idea number 2, which is particularly dear to my heart since it was my own. So if that idea was right, then turbulence would be locally unimportant, locally in this very region, if the idea is correct, and that the electron orbits should be fairly undisturbed. They can be complex, okay, with these bounce orbits, but they shouldn't be randomly scattered. So summarization shouldn't necessarily occur. And if you measure those electrons in some cool way, and then these measurements should indeed show that. Okay. So, well, so here is what MMS measures. Actually, this is not an MMS data. This is a data from my peak simulation, but it's basically the same thing. It illustrates the kind of measurement that we've been doing. So, which we call a distribution function. Those of you in space physics, of course, know that very well. But for everybody else, the distribution function is a fancy name for a probability distribution to find a particle at a certain velocity in phase space. So in this case, we have a z velocity, which is up and down, say, and x could be left and right. And the color here indicates the amplitude, if you want, and the amplitude indicates probability. So dark means no particle, or very few. And bright yellow or white indicates high probability of finding particles. And indeed, you can find complex distributions like this. Fortunately, the one that we're going to be looking at isn't quite as complex, but that's the basic idea. You know, we need to understand these distribution functions. We need to measure them. We need to understand them and relate them to this idea of bouncing particles to see whether this idea is right. Okay, so how do we do this? Okay, so here's a simulation of magnetic reconnection of at the magnetopause. So we have this is turned sideways now. This would be the Earth would be up now, and the sun would be down. Here's the Earth's magnetic field. Here's the what we call the magnetosheath, the part of the sun's magnetic field that impinges on this magnetopause at this boundary. And here reconnection is occurring. Here's our little diffusion region. And here are jets, okay, and newly reconnected magnetic field. So we're going to use that as simulation as a basis to investigate this a little bit from a theoretical point of view. We take one time. Here our magnetic field is to the right, here's to the left. It's of different strength because it's asymmetric, which is the generic situation in cosmic plasmas, I would say, unlike in the night side magnetosphere where it's symmetric. And here's our diffusion region. So now we're going to look at this again from a slightly different point of view than we did before when we looked at electrons in this electric field. We're going to turn it around again. Here we go. And here we got the current that I mentioned before because the magnetic field reverses and we got lots of hot electrons. So if you got electrons here, okay, then you know if they're moving up and down, they will enter this region or get turned around and enter this region, get turned around as well by the magnetic field. So we're going to look at the upper region first here. Okay, so let's say we have an electron that's coming from this layer here of heated electrons and current, and it's going up and it's entering this magnetic field, which you have to imagine, of course, extended to the right and to the left here. I only drew sort of one value of this y coordinate. Okay, so this magnetic field here and here too, of course. So it goes in here, it gets turned around, and it goes back. Trivial, right? It's like a half of a Lama orbit. Nothing to it. So cool. If we get that, then let's say we understand here. Obviously, the velocity is up. This is VZ. This is the up and down direction. It's positive, and on the other side, it's obviously well, I guess I forgot the horizontal part. VZ is 0, and Vy, the velocity in this y direction, is less than 0, and on the other side, it's going down. So VZ is less than 0 again, and Vy ultimately could be smaller. Okay. So good, very simple. It's nothing but a Lama orbit, kindergarten stuff, right? So, but there are more. This is an electron of one specific energy. So let's add electrons with larger energy. So here's one with a larger energy that goes further out. Again, keep in mind there's magnetic field everywhere here, just not in the middle. Okay, so this goes out this far and goes back. And if we get this guy, then we get an electron that goes far in and comes back further out, but they do come back. Okay, so let's see, what will we measure? Let's say we measure at some specific Z value here. Okay, so here's our measuring box. So then if we look at higher energies here, then we're going to see VZs, velocity in the Z direction, that are positive, that are going upward here. And as we go to lower, and oops, sorry, that's not what I wanted. No, I messed it up. Sorry about that. So if we go to lower energies, then we get more and more, less and less VZ and more VY here, until we go to the other side of the VZ velocity, if you like, where we find negative VZs that correspond pretty much to the positive VZs. So what would that look like in a distribution function? So there's a high probability for certain energies going up and then being horizontal and then going down again, okay? So here we go. This is what that looks like. Believe it or not, it does. So this is distribution function, is a distribution function that is based on electrons that are only coming from this current sheet. Here's our Vy, the horizontal direction, and here's Vz, the up and down direction. So let's explain this, okay? So if you look here at this, if you like, peak of this crescent, as we call it, we got no Vz, okay? But minus Vy is maximum. So Vy is maximum negative, okay? And if you go here, you see the energies are slightly higher. If you look at the velocity squared, these particles here, they're still going up to higher Z values. They're on the way up because Vz is positive, okay? They already have a Vy, so they're starting to turn, but they're still on their way up. And down here, okay, they're returning. They're negative Vz, so they've already been at their peak, which was slightly high energies for these particles, and they're on their way down again. Quite simple. And this is actually a result from a simulation. So that's almost the complete distribution. Okay. So what we want to do is we want to make it complete. And for the completeness, we need to add the electrons that are on their way in from above. Those are relatively simple. They're just gyrating around the magnetic field and drifting downwards here in the overall reconnection electric field. So if we add that, we get this distribution function here, which has all these features, plus this core here, which is incoming electrons from the magnetospheric side of the model in this case, right? And this we call the crescent. And you can imagine if something like that exists, then of course the particle orbits have to be quite regular. So MMS was the mission, is the mission, and was, of course, to study, to see whether such distributions actually exist. So, and it did. Oh yeah, incoming from above. So let me give you a little bit of a quick introduction to the Magnetospheric Multiscale mission. So here is a video that I'd love to show. This is a launch in 2015, which I attended. I believe Rumi attended it too. I've seen quite a few launches in my life here, but a mission that you participate in so much is seeing that launch is a very special experience. And here's an animation of what happens in space. You got the fairing flying away. You got the four spacecraft sitting on top of each other with the instruments on the side here. You got the separation of the spacecraft, and you can see how they start to fly in formation. and how the instruments start to unfold and deploy. This is the magnetic field boom here, which I believe Graz in the magnetic field instruments, Graz was participating, as well as in the neutralizing instrument and one of the electric field instruments. These electric field booms here that just deployed, very long wire booms here to measure electric fields in space, namely exactly that reconnection electric field. And then there's a boom in the z direction here, which is called a stator boom that deploys to measure the third component of the electric field. So, and there are 4 of those, and they're flying in formation, ideally in a tetrahedron, so we can measure variations in all 3 spatial directions. We actually managed to get these closer than 10 kilometers to one another in their science operations. Also a record. Okay, so here is here is one of the first science results that MMS had, and we call that threading the eye of the needle. It's a scientific breakthrough, and it's a paper published by Jim Birch. And the event was in October 16, 2015. Here's a more 3-dimensional sketch of the Earth's magnetosphere. And the orbit of MMS was sitting roughly like this. Forgive my limited drawing skills here, where MMS was penetrating this magnetopause roughly here, a little bit to the side from the terminator here, from the noon terminator, to observe process in the magnetopause, and it did observe a reconnection process, and it did indeed, in a paper that Jim Birch published in 2016, it did see these crescents. So here is a simulation by Paul Kasek here that shows the scenario here. Here's our diffusion region, here a spacecraft. You see this spacecraft here sits just where we would want to measure these distribution functions, and it or this one here the same, and it measures indeed these crescent structures here just the way we predicted them. The core is a little bit hotter here than in my simulation, and that is simply because the magnetospheric plasma was hotter than what I had in my simulation. But the key feature here is the existence of these crescents, which seemed to prove quite unambiguously that electron orbits were quite laminar and as predicted. So that was a great success already this early on. Let's take a look at the night side though, where reconnection is symmetric. Here we had another event, and this is a little bit later in 2017 here, the famous, some of us famous July 11 event in 2017, which was just about the cleanest reconnection encounter we have seen in the night side. When MMS was out here in this plasma sheet where we expect reconnection to occur, and it did observe a reconnection region. I'm going to take a look at that just a little bit more here. I'm going to dive into the physics a little bit more than I did before we come to an end here of this presentation. So remember, the electric field here is given by is moving things from here to here. So we need to understand this electric field, and we can do that now a little bit more mathematically. A little bit of fun at the end here. So this electric field here, remember, Z was up and down, X is to the left and to the right, and this electric field points out of the plane, and it is given by this equation, okay? So let's deconvolve this equation, if you like. So this is nothing but this V cross B term that I told you about earlier, that if E is minus V cross B, then reconnection can occur. Well, fortunately, there's some other terms here that fix that problem. So one of these terms is actually responsible, or it's a combination thereof, for making reconnection possible. So this one here obviously vanishes at an X point if the magnetic field is 0. And the velocity, which is fairly symmetric, is coming in, up and down, and going out left and right. In the middle, it's 0. So this is like doubly 0 at this x point. So it cannot provide the electric field. Well, just another way of saying E cannot be minus V cross B for reconnection. So these two terms are quite negligible here because the electron velocity doesn't fluctuate a whole lot exactly at the x point. And there's not too much variation of the electron pressure. This is the pressure tensor here. And in space plasmas, pressures are not isotopic. They can actually be very complex and have many tensor elements in pressure. So these two things are negligible. This vanishes at the stagnation point here as well for the same reason, because this colloidal velocity is 0, the velocity in plane velocity is 0. So we end up with those two terms here, which I don't think before we started looking at reconnection anybody's ever looked at. So these are off-diagonal pressure tensor elements that actually require distributions that are not only not isotropic, they're not even gyrotropic. They're non-gyrotropic, meaning they're not even looking the same as you rotate around the magnetic field. Okay, so these pressure tensor elements are really important. I could show you hours of theory about this. I won't, but I will show you that we can actually measure them. So, okay, so let's go on to this. This is a simulation here that we did to analyze this region here, and I'll show you just the individual terms here that I just discussed in terms of an equation. So if we do a cut here, then what you're seeing here is electron inflow here. Okay, here's the magnetic field reversing, and here's the electron current. This is electron flux, that's why it's negative. The current would be positive. And here's the electric field. Here's the pressure. Okay, here's a total electric field in black. Red is the pressure. And in the middle here, where we have the x point, the pressure gives you all the electric field. Okay, and the convection electric field, the V cross B term, goes as it should, just goes to 0. So this pressure term is really important. And it's a manifestation of these complex orbits. So, all right, very good. So here's what we saw. And I know those of you working in space plasmas know this event very, very well. This is the famous tail event here. What you're seeing here, L is actually the left and right component here in the magnetic field. You see that going through 0 here. So here is a potential reconnection region. The N component is the up and down component. You see that also going to 0 here. And the M component, which would be out of plane, is actually, well, not very important here. Here, the velocities of the electrons. Remember that there was supposed to be a jet. Okay, and that jet would have an X component in my coordinates or an L component here. And you see, by golly, here's your jet. Okay, so it's going to one side here. This is negative. It's positive. It's going to the other side there. So it does that for you. But the electrons are also flowing out of the plane into the M direction or into my Y direction. This is the electron current that I just showed you on the previous slide. So we have an electron current sheet as we wanted. We have a jet reversal. We have a magnetic field going to 0. Everything anybody could possibly hope for. And we got good electron measurements. So here we go. So Roy Tobert and co-workers went and studied this one. And I'm going to go to the next slide. But there were some other people who studied it, most notably Rumi Nakamura. And what Rumi did is she took those data and used them to fit to a model that we created based on estimates for this pressure tensor some years ago to estimate the value of the reconnection electric field based on the electron temperature, as well as this variation of the electron flow velocity as you go through this jet reversal, right? So this gives you a derivative, okay, and in the x direction. And Rumi did that. Okay, here's Rumi's estimate for here's the magnetic field reversal. Here's the electron flow velocity, and Rumi measured the electric field here, and it came out to be very, very close to what this estimate gave her. based on this equation. And since this equation was again based on this laminar theory, it again was a very nice proof that reconnection is indeed a laminar process in this electron diffusion region. Outside, it can be quite turbulent. Okay, you could in this case, Jan Eerdal in Wisconsin actually went to try to measure this electron pressure tensor and compare them to PIC simulation. I know that Nakamura-san at Graz has done that as well, and with great success, I might say. But there was a reconstruction of the pressure that Jan did from PIC simulations, and he compared those two measurements here and got which he could actually develop. He developed technique to get pressure tensor data out of the measurements. It was also kind of a first to give you this a variation that he expected, which kind of proved the point here. Okay, so which means that sometimes nature is really nearly two-dimensional, a surprising fact to some at least. This is a fun thing that I saw on a Japanese island called Ishigaki, the bird of paradise tree, which looks very complex, but if you turn it around, it's just a single sheet, if you like, very nicely arranged, a beautiful plant. Okay, so let's see, maybe we'll go through this really quick and then I will quit. Some open questions that we still have. We learned a lot now, of course, but there are open questions. Is the diffusion region really always laminar? I mean, I strongly believe the answer is yes. Okay, there could be, but there could be something we haven't thought of. And you know, the asymmetric diffusion region is more complex than the symmetric one. We need to work more on understanding that and developing perhaps a similar analytic expression for the electric field that we have for the symmetric one. Okay, what is the rate? How fast does it actually go? I know we have an equation to calculate it based on what Rumi saw, but can we predict it theoretically? And I'm sorry, Ishin Liu and co-workers actually did some work on that in 2017 and quite recently, and came up with a theoretical prediction that is basically based on the magnetic geometry around this exponent region here to predict the magnetic reconnection rate of the value that we actually see, because it always appears to be the same value, always. No matter where you are, no matter what the circumstances are, it always comes to this value. That's something we need to finally understand. How is energy conversion happening on large scales? You know, the electron diffusion region is, you know, it's really, really small, so it cannot play a role in large scale energy conversion because it's way too small. It makes it possible, but it doesn't do it itself. So if you convert energy on much, much larger scales, the scales of the magnetopause or so, then you need other processes to play a role. There are things like electrostatic turbulence that can do electron heating, or ion pickup processes that can heat ions, but I don't think the last word is spoken there yet. There's more work to be done. And then on the latter, if you want in many ways, the most exciting things is micro-macro coupling. You have this really tiny, tiny process that controls a very, very large volume, which is perhaps a classical example of micro-macro coupling. So related to that, what do inflow conditions do? Geometry of inflow to reconnection. And how does reconnection shape its own environment again? And how long are reconnection lines and why? We're making progress on all of those, but we're far from done. For those who like substorms, you know, here's our AL index here. Why does reconnection start or not? You know, why doesn't it happen in lots of places and only in some? And how does it stop again? Why does this activity suddenly go down? Here's an example that was done by Paul Tenfjord in Bergen, where cold protons were injected into the reconnection process. And of course, that slows down reconnection quite dramatically. And then, you know, we have in the solar corona, we have lots of little reconnection events, and we also have them in the magnetosphere. But something happens sometimes, and they organize somehow to a large-scale eruption, a substorm in the Earth case, or a solar eruption in the solar environment. How does that happen? You know, how does this organization happens? We don't understand that, okay? Very important question. And finally, something really dear to my heart. There's some of us who think, me being amongst them, that auroral acceleration, you know, the beautiful auroral displays that we're seeing, if you're traveling far north or south, that they could actually be a result of a reconnection process, because we get magnetic fields that are, the Earth's magnetic field is pointing up and down, and it gets sheared, you get current layers, reconnection can occur, and you saw that that accelerates electrons. And these electrons can precipitate and cause this auroral display. So that's something that we're actually studying by means of an ISI team. Okay, I think I've probably overstayed my welcome a little bit here. So reconnection is kind of the engine behind what we like to call magnetic explosions in space, but also in many astrophysical plasmas. And we have now a fundamental understanding, and the most fundamental understanding perhaps ever, how reconnection works. Courtesy of the MMS mission, we're ready to do more, and there's lots of fun things to